recycling of plastic is a bunch of nonsense. You say, why would you say that? It's because brand new plastic and recycled plastic are the same price. And you can't use reprocessed plastic for anything food related or pharmaceutical related. If you think of what's done, the plastic comes in, human beings stand there and they separate the 7 different kinds of recyclable plastics. And then there's other plastics that are not recyclable that get put off to the side. Then of those, say, high density polyethylene, milk jugs and detergent bottles. And then that goes to a recycler, it's chopped into small pieces. And then it's washed 3 times with hot water and detergent. You think there's a cost in there? Yeah, there's a cost in there. And so you calculate all of the energy in that, and it's not doing any good to the environment. It's just to make us feel good. We're going to learn about flashing, this flash Joule heating. It can be used to make graphene. This is probably the biggest discovery that I have had in my group. This ability to use flash Joule heating for synthesis. It's really, really big. The extent at which we can proceed with this is really quite large. And what this opens up, I mean, we're discovering all the time what this is going to open up. Now, flash Joule heating has been around a long time. And we'll see that as we go on. I'll show that in just a moment. Remember we talked about laser-induced graphene? Here's the guy who discovered laser-induced graphene, Jian Lin, or goes by Javan. He's now a professor at the University of Missouri. And he was the guy who was trying to hit graphene oxide with a laser that's found in every machine shop, and it missed the target and it hit the polyimide sheet. And that then turned black, and he analyzed it, turned out to make graphene, which is the most popular way now to make graphene. He's the guy who did that, so you can put a face to that. Here's another face. This is Rockwen Yi, or he goes by the name Moon, and he was the one who discovered the graphene quantum dots in coal, that student that did this. And he just got promoted, so he's an associate professor at the City University in Hong Kong. Remember the rat that was restored? Dmitry Kosinkin was the one who figured out the way to make the graphene nanoribbons. Boštjan Ganario he's actually now been promoted. He's an associate professor at the university here in Slovenia. He was the one who figured out how to alkylate the edges. And then William Sikkema was the one who started applying this to the melding of spinal cords in our group. So I'm just putting some faces behind some of the things that you've seen. Now, what is Joule heating? Joule heating is just resistive heating. So you're just putting a current through a resistor and it's going to get hot. And your toaster is an example. So Joule heating's been around for a long time. Put electricity and things get hot. Same with a light bulb, it gets hot. So Edison was doing this thing. And but the idea is to take some material, put it between 2 leads. The material has to be somewhat conductive because we're going to drive a current through this. You don't want it too conductive because it's just a wire, the current goes through, you don't get much heat. So you want something that's somewhat resistive, somewhere around 1 ohm to 50 ohm resistance. And then you will get heating, particularly at hot spots. So we're going to put a powder in there, and so you're going to have these powder particles. At these points where it's touching, there's a little bit of resistance at these points as these are touching, and it's those that are going to generate the hot spots, and this is going to get hot really fast. And so here's the person who discovered this in our group, Dui Luong. He discovered this in 2018. We immediately filed a bunch of patents around this idea, and that is the genesis of this company that we'll see in just a moment, Universal Matter, which is probably, I certainly hope, but probably going to end up making a lot of money because of what's been developed here. And what he did is he put some carbon between 2 electrodes. So this is a quartz tube. Put some carbon between 2 electrodes, and he put a high voltage and a high current across that material. Here's an important question. Why would anyone believe that a man named Jesus died and rose from the dead? If you don't believe in the physical resurrection of Jesus Christ, send an email to tour@drjamestour.org and we'll set up a meeting and I will tell you about why I embrace the resurrection of Jesus Christ. And he put in enough energy such that there was so much energy in this that every carbon-carbon bond breaks. What he used was carbon black. So every carbon-carbon bond breaks. The non-carbon elements sublime out. They could sublime out the sides here. They go out the sides here because these electrodes are not tightly fitted in here. And so then what will happen is the carbon, every carbon-carbon bond breaks, and then it reassembles upon cooling. It reassembles to the thermodynamically most stable arrangement of carbon atoms. And that's graphene. And so you get graphene, just like that. Now, if you look at this, this is a time in seconds. So this is 3 milliseconds. At 3 milliseconds, it's heated to over 3,000 Kelvin. 3,000 Kelvin is almost the same as 3,000 centigrade. They're only 273 degrees difference. So when this is like 3,200 Kelvin, so it's about 3,000 centigrade. That's screaming hot in 3 milliseconds. And then it cools very rapidly too. Then it cools very rapidly. And you see a big burst of light when that happens. That big burst of light, that's called black body radiation. And that's just a lot of the energy is coming out as light. This heats so fast. If you have a small sample here, say like 50 milligrams, it heats and cools so fast. There's been almost no heat transfer to the quartz tube that's around it because it was so fast. And so that quartz tube is only warm to the touch after the inside has been to 3,000 degrees. So you see it's very different than heating in a furnace. A furnace would make this such that you have to heat a big furnace and keep this thing hot. This is a lot of energy, but for a very short amount of time. So it turns out that the amount of energy that you're actually putting into the sample is overall very little. It's a lot, but over a very short time span. And you get this big flash, and that's why we named it flash graphene, because for something to take off, you want a good catchy name. That's what you want. You want a good catchy name. And flash graphene, it gives flash, and people will think about it, the flash graphene synthesis. And this is what the graphene looks like. And you can see this pattern here. So he did a bunch of Raman spectra, will tell you the quality of the graphene, and you can see the quality of the graphene and some of the best graphene that's ever been made, the quality, has been made now by this procedure because it got so hot. Remember, when we were growing graphene on copper, that copper was getting to about 1,000 degrees. This is 3,000 degrees, so it's really hot. It's so hot that if you have aluminum in there, if you have silicon in there, they're subliming out, they're distilling out. They'll come out about 2,600 Kelvin, and this is over 3,000 Kelvin. So they come out, and so you get a very pure form of graphene. It's very high quality. So if you calculate the amount of energy that actually went into this, if you wanted to do a ton of material, TON is ton, that's 2,000 pounds. If it's TONNE, that's a metric ton. That is 2,200 pounds because a kilo is 2.2 pounds. So if somebody says ton versus metric ton, that's just 10% difference. All right, so they're still pretty close if you have a British ton versus a metric ton. And so this is what the graphene sheets look like by TEM, so you can see that. So this is the amount of electricity that you have to buy in order to do a conversion of carbon, some amorphous carbon, into graphene. $30 a ton. Now think about the economics here. Graphene sells for $60,000 to $100,000 per ton. All right? Here you can buy coal, for example. You could buy coal, and coal costs $60 to $100 a ton. and you can put in $30 worth of electricity. So you buy $100 worth of stuff, you put in $30 of electricity, and now you have something that's $60,000. You can get up off the ground now. I know this has shocked you. This is amazing. There's no synthesis process like this that can make something for these sorts of numbers with this very small change. That's what's happening here. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. This is turbostratic graphene versus AB stacked. AB stacked means that you have the one layer in black and the second layer in dotted lines below it. So you have this perfectly offset, so you have the electron rich of this benzenoid ring over the electron deficient portion of the benzenoid ring, because the middle of the benzene ring is low in electron density. The edges are very high in electron density. So you put the low over the high, and they hold together. So they're tough to exfoliate. It's like, in a way, pulling apart Lego blocks. Sometimes you've got to kind of work at that. But if the Lego blocks are just thrown on top of each other, it's very easy to get these apart. This is turbostratic graphene, remember, where you had no particular ordering. It makes turbostratic graphene, so it's different than if you take graphite and you try to separate graphite into individual layers. There you have to invest a lot of energy to pull this apart. Here you don't have a good electrostatic interaction between the sheets. I'm trying to get you just to think at the molecular level. It's a very simple molecular level as to why a material has the properties that it does. Why does this material come apart much easier? Well, because it doesn't have the strong adhesive interactions between the sheets. So it falls apart much easier. And as you think about the molecular structure of materials, it gives you a much better view on how to, a much better perspective on the properties of the material. So for example, if you take polyesters, which may make up a carpet fiber, if you take polyesters and you think, why is it that you can walk across a carpet and it doesn't leave these massive footprints? And if it leaves a footprint, it goes away after a moment. Why is that? And that's because these polyester strands have collapsed and then they spring back. Why do they spring back? You can take a polyester fiber out of a carpet, just one thin little fiber that looks kind of like a hair. It'll stand up this high and not fall over. Why is that? Why is that? You can take a piece of thread and try to stand it up, it falls over. What's the difference? Well, that polyester fiber has these interactions between the molecular chains that are fairly strong, but they will allow deformation and it'll spring back. And so this is why you can sit on the cushion on this seat. You sit here and then you get up and it springs right back. If this were just a bunch of cotton in there, or something, you'd sit, or feathers in there, you'd sit and your butt print is going to be left in that seat. And this is why, so here you have this foam, this polyurethane foam in the seats, and this then springs right back. Think about materials' properties based on the molecular level, and it gives you a much better appreciation that why a material is what it is. Why do you run your car into a tree and your car is destroyed and the tree's just fine? I mean, it doesn't even bother it. Why is that? And it's, again, you have these carbohydrate strands and you have a lot of hydrogen bonding between these strands, so they will give a little bit and then spring right back. And that's why the trees have an amazing strength for this impact strength. Wood has amazing impact strength, and you can hammer on a piece of wood and it's there, that wood doesn't just shatter. You try to do that with a piece of plastic, hit a piece of plastic the way you hit a piece of wood with a hammer, and generally that plastic just shatters. Why? I mean, wood is an amazing material. Anyway, so so the whole group joined in with this, and he did these flashings so you can see the quartz tube, and this is just a little bit of he used a copper copper wool to plug it in there, to hold it in there, and then came in with the electrodes. So you can see the copper wool on each side. And I told them to make 1 gram, because the title of the paper was Gram Synthesis of Flash Graphene. Gram synthesis, because as soon as you can tell people you can make a gram in a laboratory in a single shot, that's a big deal. That means that this is scalable. You're not making a nanogram, you're not making a few nanograms as you do with growing graphene on copper. Here you're making bulk. Now, growing graphene on copper has its place, because then you can remove it from the copper and have a single sheet and do electronic studies. But if you want to make bulk graphene that you can now blend into materials and put it in composites, that then has this big effect. And so you can see that if you buy commercial quote-unquote graphene and you try to suspend it in water and then you centrifuge it down, it just all drops to the bottom and you can decant off a clear liquid. Here you do the same thing with flash graphene and it stays dispersed. That means that these are really well dispersed sheets, and then the surfactant was able to get in between them and keep this suspended in water. You can put it in different composite materials. So a polydimethylsiloxane, you can put some of this carbon black derived flash graphene. The flash graphene came from carbon black. You add that to it and you see it doubles the compressive strength by adding 0.1 weight percent of the flash graphene. If you just do this with carbon black by itself, it doesn't go as high. So it's better in dispersing a small amount to get the strength of plastics. Why is this a big deal? So if you can start replacing, say, aluminum in a car with plastics, and just by strengthening those plastics, that becomes very important, because remember, the whole thing about increasing efficiency is the whole thing about that is with efficiency is that you want to lightweight the vehicle. That's the thing. All right, so you can disperse it also in organic solvents. And here it is. This is weight percent of flash graphene that has been put in cement. And so if you put 0.1 weight percent in cement, the compressive strength goes up by 35%. The tensile strength goes up by almost 20% with 0.1 weight percent addition. By the time we published this paper, we had it at 0.01 weight percent. So you can see that the big enhancements that come. So what are the markets for this? It's going to go into concrete. Now, concrete is the biggest material that's used in construction. You take all other construction materials combined, wood, aluminum, steel, combine them all. You don't reach each year the amount of concrete that you use. Concrete is a mixture of cement and aggregate, and so aggregate is a bunch of rocks. So concrete is used a lot. If you can use 1/3 less concrete, that is a big deal. Why is that a big deal? Well, concrete, the making and pouring of concrete is 1/3 of humans' CO2 emission. So if you look at all the CO2 emissions that we as people put into the atmosphere, 8%, not 1/3, 8% of CO2 emissions is the making of concrete. And the reason for that is you're taking metal carbonates and you heat them up. And from that you get metal oxides, and you're blowing out CO2 in the process. Those metal oxides are making your Portland cement. And then you take that cement, you add in rocks, and you add in a lot of water, and you cook this thing, and so you're heating this thing. So you heated it up to 2,000 degrees to convert the carbonates to the oxides. That put in a lot of energy. And now you're mixing a lot of energy. Then you put it on a truck, big truck, a lot of energy. Bring it out, turn that thing, and then drop it into the ground. It's a huge amount of energy in the concrete business. A lot of CO2 emissions, and if we're going to deal with CO2 emissions, now some people think that CO2 is not a problem for mankind or humankind, it's going to be just fine, and maybe that is. I'm not taking any stand on that. I'm just saying is if we want to reduce CO2 emissions, dealing with concrete, and you have to take big steps. Dealing with concrete is a big thing. This is the evolution of how he did this. And so his first ones here, where he just took 2 electrodes, and this is a capacitor. And he just put a little bit of carbon black between 2 electrodes in the open air and hooked this thing up, and you saw this poof. He looked at the Raman spectrum and he saw a little bit of graphene, and he optimized from there. And so he then took a quartz tube, he put the sample in there, put these wads of copper wool, and then he just took brass screws and stuck them in the ends as the electrodes. You see the brass screws? And then how are you going to keep this pushed down? So he just put electrical tape around it. Just kind of push it in there. And he would see that when he would flash it, the electrical tape would get too hot and it would just melt away. So he just put some paper in between the electrical tape and that, just to keep it a little bit off of that. Just keep it a little bit off. And he would flash like that. And then he developed this system, and finally, and then he made these little jigs that could compress from the quartz tubes, and below this was a little platform with these screws that he bought off of Amazon. And then he had the laser that we had to make flash graphene. He used that to cut wood, and he put this together and then glued it with epoxy wood. And so then it came up to this flash, which we called the Flash 2.0 system. This thing, we published so many papers from this. So the capacitors are down here in a box. That's where the charge is going to be built up. Here's the electronics in here. We weigh the sample here, and we'd flash it in this desiccator. So this little jig is inside this desiccator. You can see it inside the desiccator there, and that's where the flashing would take place. All the first papers got done with this, and investors came in and go, okay, that little bit? You think you can make money with that? I said, no, we're not planning to make money with that little bit. We're planning to make money by scaling it up. So but that's all you've made is a little bit. Well, that's why you're here. You're an investor. I mean, if we're really rolling to make money, I don't need you, right? You just start selling it. And they say, well, this is so involved. It's so involved. Remember, it's so involved. And you need to go on YouTube and see how a pencil is made. Would you consider a pencil a very sophisticated object? Generally not. But go look at the number of steps involved in making a pencil. You have to take the graphite and you mix it with an inorganic, and it's baked together. They make these long rods of this graphite. Then you have to take this wood, and the wood is cut down, and this is put through the middle of this, and then it's cooked and it's painted, and you have to put that little metal cap and then the rubber thing. It's like many steps to make a pencil. But you can sell a pencil for 25 cents because it's been automated. It's been worked out. It's all been scaled. And so you can do this. So this is the 2.0 system, and we put a little warning light on there to tell you when the thing was charged up. So you make sure you know it's charged up. And then we had these switches, these kill switches, and you could see, and we told everybody, never go poking around down here with the capacitors. We don't want you to die. And we have a lot of safety constraints in that we want people to wear thick rubber gloves, the electrical workers' gloves, when they're working with this, and just in case. That's the last resort. The first thing is you hit the switch system, you cut it off from the capacitors, and lots of these safety things. But here's the electronics, and so you have these capacitors here, and you're just driving it with these power sources, two screws. But we published a lot of papers out of this and disclosed it to the world from this system. And here's the little jig system that we came up with, and then you turn these knobs, and it will compress this thing down. And then we built a bigger system that could be charged much faster. And this was a much later redesign that allowed us to charge much faster. We had the university bring more electricity into our laboratory to help us to do this. And this is what the big system came out. There's 48 capacitors in these 2 boxes. Each one of these capacitors is a truck capacitor. It's used to start one of those big 18-wheeler trucks. And so when we bought 48 capacitors from the company, they were out. We bought every capacitor that they had. They had to make more. They weren't used to having orders like this just out of the blue. And and then we put it all computer control. So you do this was the computer screen. You turn on the power, you charge, you can discharge it, or you can flash, and you can talk about the amps that you want to go through this flashing system. So because you're touching a computer screen, which is hooked up to the machine, you're not touching that machine ever. So you can do everything. So you see the safety that's built in when you could do this. And this was under the hood. So this was built into the hood, and this was under hood. But you can see that the types of wires, they're carrying this current to go through this. And then with an IR thermometer, we could record temperatures up to 2,500 degrees. So we could buy thermometers that would record temperatures up to 2,500 degrees. There are IR thermometers that can go above that, but they're not for people like you and me. They're for the military. And so you need some special permit to be able to get something like that. So what the student did is he built a spectrometer to get this spectroscopically to record the temperature. How do you record the temperature at 3,000 Kelvin? So he built this IR spectrometer. This is the second one he built. The first one didn't look this clean. But you just put it in like a Tupperware container, and so he built this for $1,500 rather than spending $75,000 on a commercial spectrometer. And just amazing student. Dewey Luong was just super creative, and he had all the heart to be a researcher. The guy would at night he'd just be working late, and he'd roll out a little mat and sleep right there under a desk. I mean, that's what he did. When I saw that, I knew this is the guy. This is the guy I want. He's got all the heart to do this. When you are driven passionately to do something, whatever it is, whether it's to build something or you will accomplish a lot. If you read Elon Musk's the biography of Elon Musk by Isaacson, just came out a few months back. I read this. Elon Musk often slept under his desk in all of his companies, and he was often like this, working away. And you just see the dedication. So I want you to get in your mind that this is what you have to do if you want to be successful. You have to be really, really dedicated.
I was just wondering, did they at least have a pillow?
Yeah, he had a pillow. He had a pillow and he had a little roll-out mat.
Maybe some blankets
I
too?
didn't see blankets, but maybe so. Maybe so. But it's dedication. It's really dedication. You're going to be driven for something, and if you're driven and you follow through on this, it will really make a difference. That's the key. You have to be dedicated. Researchers that do great discoveries, it's not a 9-to-5 job. It's just not a 9-to-5 job. You guys are in college. In many people's minds, going to college is a huge barrier. So, for example, my custodian, her name is Maria, and I said, Maria, I talking to her when I first met her. I asked her if you have children, and I said, are they going to go to college? She said, I don't know if they're going to go to college, so I said, bring them in here, bring them in. And so I talked to them, and I drove into their mind that you're going to go to college. This should be a natural thing. In my home, not going to college, you never even thought of not going to college in my home. You were going to go. You come from homes where college is valued. There's a lot of homes that don't realize. I want to put a new value in your mind. A new value in your mind is to be successful, you're going to have to work very hard. It is much more than 40 hours a week if you really want to be successful. And don't let that scare you. Don't let it scare you. That's just part of what you have to do. And if you love what you're doing, then it's not like being a slave. You're really excited about this, and it makes you work. And if there's anything good in life, it is worth fighting for. It is worth doing this. So get this in your mind that you're going to work very hard and you're going to be successful. And that's why God made you the way you are. You're young, you're strong. Pour that out into something productive. and you can accomplish so much. And then we wrote AI machine learning optimization programs for this because there were many knobs that could be turned. And so we used just commercial packages, but we optimized those commercial packages to be able to really push this thing along. And so this is part of what we did to optimize on this. And so then we went into this very fast charging system. So normally we buy our parts. So here's the fast charging system. You see it has a little fan built in, and we just buy these are just plastic boxes. And so these things like this, like you can have resistor arrays and things like this this is a load resistor. And we just buy them. This is bought through eBay. These are other people's waste. They're just getting rid of them. And so you buy this for like $10. I mean, this would be normally thousands of dollars to buy load resistors like this. And so you can do this sort of thing. So we buy so many things off of eBay that people are just throwing out essentially, and you pay $10 and you get this thing. And we built this, and so normally it was taking about 3 minutes to recharge the system. So then we could get it down to 20-second recharge. So it increased tenfold our production rate. And then, so then it was over COVID that he built these automated systems. I'll show you another picture of it in a minute. But all of this is 3D printed. And so when we had to get out of our lab for 2.5 months, you think we're going to slow down just because they throw us out of the lab? I bought a bunch of 3D printers and sent them home with the students. Just go ahead, keep making stuff. And then you see these metal electrodes from which we went eventually to graphite electrodes. Those were the most stable electrodes, but these have to come in from the sides, and these are all brass. Now, then we had to weigh out a lot of charges. We were using like 5.6 gram charges, and how do you weigh out a powder when you're making a lot of these to set up automation? Well, this is a bullet loader. So when you has anyone here ever loaded their own bullets? So if you've done it, yeah, and so you know what this is. This you just pour in your gunpowder here, and you program in how much weight you want to come out, and it dispenses that amount of weight automatically. So you're not, doing, so it will dispense it into this pan, and then you could load it up. So this bullet loader, this balance, if you buy, this would be like $20,000 if you bought it for a laboratory. But this gunpowder dispenser was $300 on Amazon because it's for gunpowder. It's not for a laboratory. Oop. That's the difference. If they're selling it to a laboratory, they're going to charge a lot of money. And then all these brass parts would always get crudded up with this powder, and they'd get all blackened. And so this is a bullet shell cleaner. So bullet shells, after you shoot, you get the shell and you can reload the shell, but it's all covered in burnt gunpowder and stuff. So you throw it into that bucket with usually a corn husk medium, which is kind of abrasive, and it just shakes it. And it cleans up brass, and it makes it really spick and span clean. So this is the type of stuff we were doing. Again, we were shut down for 2.5 months, but Amazon and eBay are open. So this is the system that they built. So you see that you could charge these things. One was white, one was darker, and you could charge this thing, and it would roll down here, and then it would go between here, and then it would flash, and then it would drop it off, and the thing would roll down into this pan, which is obviously a paint pan. And that was the receiver for this. And so you could see this thing flashing. It would roll in, and it would flash here, and then it would come and it would drop out of here. And this is the way it could do the system. And this is the flash, and then from here, these two brass things, there's one and there's the other. These would retract and it would fall out. It would roll out. And so this was during the closure, COVID-19 closure. So our production rate was doubling every 9 weeks. That's a really fast production rate. And it was just going up. And the Department of Energy, we were funded by the Department of Energy, and we had just gotten this grant. So this, but we just plowed right through, and we delivered, and we over-delivered. And we were able to really do this. Now, Moore's Law, you ever heard of Moore's Law? Moore's Law is that you would double the amount of transistors on a chip every 18 to 24 months. And the computer industry has stayed on that, not just by doubling the amount of transistors, but by doubling functionality in a transistor. Well, we call this Dewey's Law, because this was Dewey's, that it doubled production rate every 9 weeks. And what's the advantages of flash graphene? Well, first of all, it's non-toxic. It can be used even in medical applications. It's a naturally occurring material because it's agglomerates or the natural mineral graphite. It's a terminal natural sink for carbon. Any asset that you bring up from under the ground, any asset is going to be end up in the CO2 cycle. So whatever you bring up from under the ground, whether it's natural gas, oil, coal, if you burn it directly, it immediately goes to CO2. But even if you just make things out of it, eventually the shirts you're wearing, these are petroleum products, a lot of them. These are going to end up in a landfill, and as they decompose, it's eventually going to end up in the CO2 cycle. That's the thing. And so most of the things that we have, they're going to end up. But if you make graphene, it's very slow to enter the CO2 cycle. Graphene doesn't undergo fast microbial decomposition. If it did, we wouldn't have graphite mines in the world. Because graphite is there, we know microbes aren't eating this stuff. It can be used in composites of all types. There's no water, no solvent, no purification. It's self-purifying because all the other heteroatoms sublime out. It used to be 60 to 200 K per ton. Now it's 60 to 100 K per ton. It's come down. But here's the $35 per metric ton of coal to do this conversion. So there's Dewey. He's now the senior scientist there in the company. And here's John Van Leeuwen. He's the CEO. And this 1 ton per day, they've hit this target. They have not hit this 100 tons per day. So this should actually be changed. They have not hit the 100 tons per day. They're just hitting the 1 ton per day. And then this automated system needs to be scaled up and multiplied. So graphene can be used for so much. So it's going to be going into concrete. They've already got an asphalt product. It can triple the life of an asphalt road. Now think about that. Tripling the life of an asphalt road, how much energy that would save. Also what it does is it brings up the working range of asphalt of about 11 degrees centigrade. We don't use as much asphalt around here. We normally use concrete because it gets so hot. If you can bring this up 11 degrees centigrade, which is a lot more degrees in Fahrenheit, if you can bring this up 11 degrees centigrade, that's a big change without affecting the lower temperature working ability. You bring up that temperature. So then it makes asphalt more available to be used instead of concrete. Asphalt is it's just the slag product, the bottom of the product after they've distilled out all the lower molecular weight hydrocarbons, the gasoline, the kerosenes, and the diesel fuels, and then the home heating oils and things like that. And so whatever doesn't distill out, that's what they make asphalt out of. It's just the crud that's left over. And but this you can really put the working range. It's going into paints. It's going to wood composites, because wood composites, there's a lot of glue in here, so that you can put it in wood composites. It's going to metals. They're even planning to have a system where they can have bone composites. Now we got up to. It took us to the point where the paper that we published, we had to make 1 kilo in 24 hours, according to meet our DOE milestones. That was to take a U.S. coal product and to make 1 kilo of graphene in 1 day. What we delivered was 10 kilos of graphene in 1 day, and we delivered it 6 months early. So it really worked out well. And so this can go into different building materials, and so you can see the increase in the strength of the Portland cement and the concrete that can happen if you put in these additives. You can see a hardness increase. You can see the enhancement in different materials. Now, how is this an energy effort? How is this an energy effort? Well, we've already discussed one thing. If you're saving the amount of concrete, if a road is lasting 3 times longer, all of these are massive energy savings. But here's something to think about. So today we burn methane with oxygen and we get CO2 and water, okay? Methane plus oxygen affords CO2 and water. That will blow out about 800 kilojoules per mole of energy. All right, so that's the energy that we get out. So that's why it's negative. That's the enthalpy there is negative. So that's what we get out. The idea is, and this, all the oil companies are switching to this. They're going to take the natural gas, the methane, and they're going to convert it to a carbon solid plus 2 moles of H2. So how do you pull the hydrogen atoms off of carbon? There's actually a lot of ways to do that. One of the ways that's being used today is you bubble the natural gas through, bubble the methane through a molten salt, and the carbon will drop out of that and the hydrogen comes out. There's other ways you can do it with catalysts. That's actually been around since the 1950s. It was called furnace black. They just didn't know what to do with all this carbon. And then you can take that hydrogen, mix it with oxygen in a fuel cell, and get water as your only product. So you're not blowing out any CO2 in that. So overall, methane plus oxygen is affording carbon solid plus water. That's about 400 kilojoules per mole. So it's half the amount of energy out, right? Half the amount of energy out. Well, why would you do that? Well, because it's so much cleaner. There's no CO2 emission in that, very little CO2 emission in that. But this is the thermodynamic numbers. Those thermodynamic numbers are not real numbers. They're not real things that we have to deal with normally. If you look at the efficiency, you have to take into account efficiency. So your car is 25% efficient in town. So meaning that of that energy to propel you forward, only 25% of it is propelling you forward. The rest is, it's a big heat engine. I mean, your engine gets really hot. So it's doing a lot of things. It's just generating a lot of heat. This is 90% efficient in stripping the hydrogens off. This is 80% efficient in a fuel cell. So when you look at efficiencies, these two numbers come out about the same. So you get the same amount of energy out by doing this two-step process. And that's why the oil companies are all switching to this. And if you look at the carbon hub here, there's a big effort at Rice called the carbon hub. That's to do this type of thing, to think about differently. Rather than combusting hydrocarbon resources, how could you use them differently? And that's the idea behind it. But now the question comes, what do you do with all this carbon? What do you do with this? If you just throw it out and plants take it up, it's going to end up in the CO2 cycle anyway. Plants will take it up, the plants die, turn into CO2. What do you think you do with that carbon? I wonder what. Flash graphene. Because now you can put it in building materials. So if people are emitting 30 billion tons of CO2, now it's a little more than that, but just say 30 billion tons, that would be 8 billion tons of carbon, because you just take off the 2 oxygens, and so that'd be 30 billion tons of carbon. What are you going to do with 30 billion tons? We want to make it into flash graphene. And so here's these numbers, and again, these are older numbers, but you see here's all other building materials combined. Here's cement and concrete. I mean, so these numbers are just swamp out anything. These are millions of tons, 40,000 million tons of concrete. It's a lot of concrete. And the embodied energy is 26 billion gigajoules. And all of this embodied energy is 18 billion gigajoules. So, you know, it's a lot more than all of these put together. Well, where can you put 8,000 million or 8 billion tons of carbon? You could put it in concrete today. You could do that. You just disperse it in concrete. Or you can use it, and therefore you would use less concrete. But it's to use it wiser. You put it in graphene, yeah, and put it in concrete, put it in other building materials. Such that I think when you guys are my age, graphene's going to be in everything. Graphene's has been in every Ford motor car, every Ford car since February of 2020. Every Ford vehicle. It's in the foam cushion seats, and it's in the underhood insulation, and it's growing because it lightweights the vehicle. All right, so how's this an environmental effort? Well, food, 30 to 40% of all food worldwide is discarded. You say, well, why is such the way? Why? Americans are just so bad. No, this is worldwide. It's because it goes bad. Have you ever cleaned out your refrigerator and thrown out food? Ever? Who hasn't? Because if you eat that stuff, you're going to die. You're going to get really sick. I mean, food goes bad. You got to throw it out. And and food companies have contacted me. They're not happy about it, but they throw out so much food. And restaurants. Bernie, what happens to the food from the serveries here?
Yeah, they throw it away.
They throw it away. You know, I mean, you guys want it the next day, and the next day, and the next day, and the next day. I mean, at some point, you got to throw it out. You might be able to, I don't know, make a casserole from the next day, but then what do you do with the casserole that's not eaten? When do you convert that into? At some point, you got to throw it out. So this forms not just methane in landfills, this forms also CO2. And then you have rubber tires. Rubber tires are not that big of a problem in the US, but overseas is still a huge problem because we pay for rubber tires disposal when we buy the rubber tire. There's that few dollars fee that we pay on every tire. And that tire is usually chopped up and put in concrete roads and things like that. But we can make graphene out of rubber tires. We've done it. We've made graphene out of food waste. Here's plastic. Plastics, as you guys know, is a big, big problem, particularly in Asia. Mismanaged plastic is a huge problem. You can take, and the problem with plastic, again, I don't want to burst your bubbles, but recycling of plastic is a bunch of nonsense. You say, oh, why would you say that? It's because virgin plastic, brand new plastic, and recycled plastic are the same price. And the new plastic is much, much better. It's much better. And you can't use the reprocessed plastic for anything food related or pharmaceutical related. And if you think of what's done, the plastic comes in and it's all different plastics. And so human beings stand there and they separate the 7 different kinds of recyclable plastics. They stand there and they do it. And then there's other plastics that are not recyclable that get put off to the side, all right? Then of those, say, high-density polyethylene, milk jugs and detergent bottles, they take that and then that goes to a recycler. It's chopped into small pieces. And then it's washed 3 times with hot water and detergent. You think there's a cost in there? Yeah, there's a cost in there. Then they take that and it's dropped through transparent plastic tubes. Dropped. These little pieces of plastic with holes in the side of the tube. And whatever is not falling at the rate that high-density polyethylene plastic should fall, a little puff of air blows it out. That's paper, that's aluminum, that's some other type of plastic. So that's how they do it, by density of falling separation. Then they take that and they melt it all down and they blend it up, and it's got all sorts of colorants in it. So, you know, the plastic you get from the processors isn't, you know, white like what you get in the virgin plastic. And then it's ejected in these long pieces, and then it's chopped up and you get these little pellets. That's what's done. And so you calculate all of the energy in that, and it's not doing any good. It's not doing any good to the environment. It's just to make us feel good. Here's all the different types of plastic, recyclable plastics. Here's the 7 different types. We can flash all of them. This is the graphene spectrum. All of them turn into graphene. Or you can take the mixture. There's no humans separating these. You take the mixture of them and it forms graphene because you're breaking every carbon-carbon bond anyway. So we've done this with carbon black, anthracite coal, calcined coke, used coffee grounds. We had an undergrad would bring in the used coffee grounds. Charcoal, biochar, humic acid, keratin, which was human hair. Did this with human hair. Lignin, sucrose, starch, pine bark, olive oil, and so on. So you can do all of these things. You could take a person and turn them into graphene. So rather than just combusting them and turning them into CO2 and water with a little bit of residue at the end in cremation, you could turn them into graphene if you wanted to. I'm not saying we're going to do that. I'm just saying you could do that. And it'd probably be a much more useful enterprise to turn them into graphene, and then they could have some utility after they die. Strengthen your roads, strengthen your bridges, you can build your home, with this graphene. And it's just something to think about. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.